here, let's see, yeah, here we go. So here's what we were talking about last time. We were talking about how to view divergence as flux density. And I think this is a really valuable point of view. There's a lot of great intuition in this. And you'll recall that, at first I gave you sort of an algebraic justification when I started with this analogy with interpreting the fundamental theorem of calculus as a statement about this accumulating quantity of change. Right? And again, I pose it's an accumulating quantity. We don't think of change as something that accumulates over the interior. We think of change as something that we measure at the endpoints. Until you, oh man, I hit the wrong button. Here we go. Until you think about, what might be changing. And even though, you measure change on the boundary, right, here's how you measure change. That it's measured on the boundary, is perfectly reasonable to think of change as something that accumulates over the interior. And my silly example is my height as it increased from age 2 to 20, right? Of course, the total change is the sum of the individual changes that happened each day along that process. Perfectly reasonable. Downright important to think of change in that sense, right? So I'm proposing that you can think of divergence in the same way. So here's an analogous picture. Now, we talked about this picture last time, and I said I'd expand on it a little bit. So let me do that now. So my assertion is that even though we measure flux on the boundary, you can think of flux as something that accumulates over the interior. Now, algebraically, we kind of know that's true because that's what Gauss's divergence theorem says. We justified Gauss's divergence theorem by observing that flux literally accumulates, right? The flux on a whole thing, outward-oriented boundary flux through a whole solid, if you cut that solid in half and make it two solids, right? Well, the flux through the boundary of this solid and the flux through the boundary of this solid, they're largely the same surfaces of flux. The only difference is the cut surface that you created, and any flux that's going out of one is going into the other. And so the flux, on that cut surface, the flux oriented that way and the flux oriented the opposite way cancel. Right? So from an algebraic point of view, of course, flux accumulates. So I just like to point out how you can kind of visually see that in pictures like this. So let's talk about, now this vector field that I'm going to work with is, I've manufactured this for ease of visualization purposes. So my vector field is intended to be constant over here. It doesn't change in that whole region. It's just, short vector directly to the right. It's intended to be all constant over here. Longer vector, again, directly to the right. Right? This is a pretty simple vector field. But in this region, this is where the vector field is changing. I mean, it starts off short as it was over here, but it ends up long as it is over here. Right? So this is my vector field. It's constant on the left, it's constant on the right, and growing in the middle. Okay. All right. Now let's think about what can we say about this vector field. What is the divergence at different locations? Now, to talk about the divergence, I'm going to zoom in a couple of notches just for sort of visual convenience. Now, again, apologies that this is a two-dimensional picture. The main version of Gauss's divergence theorem, of course, is three-dimensional. It's just really hard to draw three-dimensional pictures with all this stuff going on. It ends up, I tried. It ends up being a muddled mess. All right, so I'm going to draw the two-dimensional version. Think three-dimensionally, please, right? But it's just much easier to draw the two-dimensional picture. Okay, so let's go over here to this side, and I'm going to draw a little region here. Now, of course, I draw a little rectangle. Please think box. Right? Okay, so let's talk about boundary flux. What's going on with the boundary flux here? Well, we have these field vectors. This field vector here, for example, and it's the same field vector everywhere in this whole general vicinity. It's the same field vector everywhere on the box, everywhere on the boundary of the box. Of course, we're looking at boundary flux. So we are going to get at these points field vectors going outward through that boundary of the box. On that side of the box, we're getting positive flux. Right? But here's the thing. On this other side of the box, over here, the exact same vectors going inward. So on one side, we get outward-oriented flux. On the other one, we get inward flux. This is a box. That means the areas are the same. So the areas are the same. The dot products are negatives of each other, so those fluxes cancel. Now, what's going on the sides of the box? Well, on the sides of the box, there's basically nothing going on. There's no flux happening on the sides because they're the dot product with the normal vector. Remember, our normal vector is always perpendicular to the surface. Field dot normal vector is 0. So there's no flux happening on the sides. There's canceling fluxes happening on the front and back surfaces. Grand total, no boundary flux. Okay? So there's no flux. I mean, you look at what we have in the green here, and in the green, there's we see an accumulation of flux over this interior. There's a lot of flux that's accumulated. It's not happening there. Where my purple box is, there's no flux happening there. Now I can make a very analogous argument, or to take this box and slide it over there. Pretty much the same argument. Constant vector field. There's a certain amount of flux out, there's a certain amount of flux in, but it's a constant vector field, so it's the same amount out as in. Along the sides, again, the dot products are 0. There's no flux happening on the sides. So there's no flux happening there either. But let's think about over in here now. And I claim that there is flux happening there. That's where the flux is happening. This flux that you see, that you detect on the green boundary, is actually happening in this gray zone. Let me just sort of, again, draw you the pictures, persuade you that this is the case. Again, let me zoom in for drawing convenience. Okay, so let's make the same kind of an argument. Let's look at the right-hand side here. Well, here there are field vectors going out. There's a positive amount of flux on that side, right? Because my normal vector is like this. Right, so there's a positive amount of flux happening there. Now, sure, there is a negative amount of flux happening on the back side, but the thing is, on the back side, the field lines are shorter, right? So there is a smaller negative flux. Negative, because again, normal vectors are always pointing outward. So we have a larger positive flux on that face. We have a smaller negative flux on that face, and those do not cancel. When you add those up, you get some positive quantity. Right? There's a grand total positive amount of flux through that little purple box. Everybody on board? Okay, yeah.
So if you had taken, if the overall green boundary was just to the right of the gray thing, like only the constant either side, the flux will be 0 either way.
So you're talking about like over in this area?
If that was
over there,
it's the whole box was the green system.
Yeah. So let's. So you're getting ahead of me. Yeah, good observation. I think what you said is correct. But let me get to that. Okay. So what we've got here is that there's a certain amount of flux that we're detecting here on this boundary, and where is it happening? Well, it's not happening here. It's not happening here. It's happening in here. And now, how much flux is there actually happening? Well, let's look at the big box, which I think is what you were talking about. The field vectors over here, the field vectors are long. We have our normal vector, right? So we have a large positive amount of flux happening on that edge. There's 0 flux happening on those edges. Again, you're going parallel, not through. And then look at these itty-bitty little short little vectors over here. Teensy weensy. Right, so there's a negative, there's a negative flux happening on the left side. There's a positive, small negative amount of flux on the left side, a large positive flux on the right side. Grand total around the green, the actual whole boundary, the total flux that we measure is positive. Yeah? Is everybody on board? So where does that positive flux come from? It comes from the gray region, right? We agreed that there's no flux happening in here. There's no flux happening in here. The flux is happening in here. Now, what does divergence do? Divergence measures exactly that. Right? So when we say that boundary flux is a triple integral of divergence, you can see right in this picture what it is that divergence is measuring. Divergence is measuring how much the flux that we measure on the green boundary, how much of that flux is actually happening where you are, right where that divergence is being measured. Right? In the same way that the derivative is measuring how change is accumulating. Now again, I love the analogy here because we all have lots and lots of experience with this idea of change. We didn't say in our minds the word accumulation, but come on. we know that stuff gets bigger over time. The total amount that it got bigger is the sum of how much those little bitty changes of how much it got bigger each day. So in the same sense that the derivative is measuring, locally, at a given moment, how much change, here let me use colors, how much change per unit size of the piece of domain, the derivative is measuring, wrong color. The derivative, that slope is measuring change per unit size, accumulating quantity per unit size, change density. Right? The derivative does that. You can see it. In the exact same way, divergence is measuring flux density. It's flux is the accumulating quantity instead of change. Divergence is what measures it locally instead of the derivative. Okay. So, anyway, like I say, I'm a big believer in this idea of thinking of these integrands as being densities. Let me go back to the book here. Seems a little weird, I grant you, to think of the derivative as being a density. Thinking of the derivative as being change density. What an odd choice. But the more you dwell on this, the more you internalize and get comfortable with this idea of thinking of the derivative as change density, you've got then a metaphor for thinking of divergence I didn't write it on the same page, but anyway, thinking of divergence as flux density. Let me go back to the formula because this is where it's really happening. Accumulating quantity, triple integral of a density. Okay, anyway, I'm a big fan. I encourage you to dwell on these ideas, let them soak in. A lot of good intuition to be had there. Okay, so we're going to go on and talk about a little physics now. In fact, this is kind of physics day. It seems to turn out that there is a single day of the class where all of the physics related to the Chapter 6 material kind of comes up. And there's a lot of big ideas here. Specifically, what I should say, the physics ideas that relate to Gauss's divergence theorem. And it's one of the it's arguably the biggest, in terms of physics applications, the biggest theorem in the class. Possible exception of maybe fundamental thermal line integrals, but I don't know. I think I'd give it to Gauss's divergence theorem. It's a lot of stuff here, largely because we live in a three-dimensional world with three-dimensional things in it, right? And Gauss's divergence theorem is a theorem about three-dimensional regions, so it's pretty natural to think that physics stuff would come up. Okay, so different interpretations I want us to take. So let's talk about fluid flows. So imagine some fluid flowing around. Now there's different kinds of fluid metaphors that I'm going to talk about because there are different kinds of fluids that run around in the world. different sorts of features that they have. Right. So the first feature that I'm going to talk about is a fluid that's where there's a fixed amount of it. That's pretty plausible, right? So you imagine maybe that we've got some region of space here, and there's a certain amount of air in there, and let's pretend that there's no spontaneous generation of air momentarily, right? So there's a certain amount of air inside of this, sphere or whatever. And now imagine that the flow of this fluid, this fluid being air, imagine that the flow of the fluid is like this. Right, so the fluid's going sort of outward, emanating outward from some central point. Let's think about what that means. I mean, how would we write that down? Fluid emanating like this. I mean, what do we get from this? Okay, well, here's what we get. By the way, did I? I'm gonna have to be careful there and not erase my little figure. Okay, so here's one thing. Mass is a triple integral of density. That's a true fact about any mass, right? Here we're talking about this fluid of air. Okay. Now I'm going to execute an algebraic choice here where I'm going to take that equation, I'm going to take the derivative and then multiply by -1. And so this gives me another true fact, right? Mass is triple integral of density, and I just take a derivative and throw on a minus sign. Still true. And having done so, let's think about what this is. This says negative dm dt. So dm dt addresses the question of, let's see, how much mass is there in here? Dm dt would say, what's the rate of change of the amount of mass in there? Well, the thing is, the mass is emanating out, right? The rate of change of that mass in there is negative. Right? In fact, the negative of that rate of change of mass is exactly the flux, right? So the flux, we think of the flux as being all of this. The flux is how the mass is decreasing inside of that region. Yeah? There's only so much air. If the air is leaving, then there's less air. Yeah? Is this a harmless observation, I hope? All right. So, having gotten that, this again came right from there. There's no contest there. We just agreed that derivative of mass is the negative of the flux. Well, flux is a triple integral of divergence of this vector field, and this gives you this little result that so the integrands of these two triple integrals have to be equal. And this is giving you an interpretation of divergence. If you want to think of, we got this vector field representing air flowing, however it's flowing. What does divergence represent in this physical metaphor? Divergence represents the rate of change of density. Well, it's the negative of the rate of change of density at a given location. So there's a certain amount of air inside of here, right? We've agreed that the air is, let's say, going out like that. Grand total, the amount of air is decreasing, sure. But what about, at particular points? Depending on how the air is flowing, what's the air density, the air pressure at a particular point, right? It might not be that the air is exiting uniformly. I mean, maybe some weird reason, maybe the air on the right side is what's flowing out, the air on the left side is not. I don't know. Let's just say. All right, maybe the air near the edge is leaving faster, and the air in the middle isn't leaving as fast for, gravity reasons or something like that. Who knows, right? So if you want to understand specifically, not just in total, grand total, how much mass is leaving, but how is the density of air at any particular point changing? Divergence tells you that. So this is one physical application or physical interpretation of divergence in this context. Everybody on board? All right. Now, let me switch it up a little bit. I'm going to continue to talk about fluid flows. I want to talk about a different kind of a fluid flow. Not all fluids have this feature that we just talked about. We were talking about the fluid as being there's a finite amount of it. There's only so much air, right? And if the air starts emanating out, well, less air. Okay. Here's another situation to entertain. What if air is being spontaneously generated? What if, there's somebody left a couple of, one bucket of liquid and another bucket of liquid, and somebody poured the one into the other, and there's a chemical reaction of some sort, and some gas, I don't know, maybe not air, but whatever. So I'm going to say air for convenience. Air is just emanating out of this bucket, spontaneously generating air. Okay. Totally different from the context that we were just thinking about. Okay, so what I am going to require for the purposes of this discussion is that we're in a steady state situation. So I want to consider that there's no sort of, the gas is not sort of in the process of accumulating in one region, and it's not in the process of, exiting, from, evacuating from some region. So I want to consider a steady state where, yeah, sure, maybe gas is flowing. We have a spontaneous generation of stuff, but we're in a steady state circumstance. Okay. All right, so now let's look back at this picture. Right, again, spontaneous generation of stuff. Here's our little region, and I appeal to your physical intuition. If stuff is being spontaneously generated, it's got to go somewhere, right? And it's got to go away, and away is outward. Okay, yeah? So now what sense do we make out of this? Now again, same picture. It's morally the same picture that I just drew here, but we're making different assumptions about what's happening with the fluid, and so we have to make different interpretations of what the math means. So here, there's no compression or decompression, right? All densities are fixed. But there is spontaneous generation of stuff. Okay, so I'm going to start again with an uncontroversial equation here. That just says mass is triple integral of mass density, right? Mass density is mass per unit volume. Uncontroversial. Again, I'm going to take a derivative with respect to time. Now, the time derivative on the left, I'm going to put in the normal place. The time derivative on the right, I'm going to talk about the time derivative of the mass in that numerator there. And you can, of course, put the derivative anywhere you'd like. It's just a derivative. Okay, having done that, we get this equation. And again, we can connect this to the divergence theorem. Let's think about this rate of change of mass. How fast mass is flowing out of this region? Well, in a steady state, the rate at which mass is emerging out of here is the same as the rate of that mass is being spontaneously generated. It's spontaneous generation of stuff. That stuff goes somewhere, right? So the rate at which stuff is going somewhere is the rate at which mass is being created. And that gives us then this equation. This says that the rate that mass is being created is equal to the flux. No minus sign here. Right? The mass is actually being generated. So positive flux means positive generation of mass. Okay. All right. Again, flux, triple integral of divergence. So we got to here from an old formula by taking the derivative. This is a statement about where stuff goes when you generate it. And here's our good old Gauss's divergence theorem. And again, we get a result. Here it is. The result is that divergence in this context is interpreted as this thing. And let me zoom in on it. Divergence says per unit volume, what's the rate at which mass is being spontaneously generated? Right now, if you talk about how much mass is being spontaneously generated at a point, well, a point doesn't have any room. There's no room inside of a single geometric point for there to be any mass. So you can't talk about how fast is mass being created inside of a point, but you can say at a given location, if I were to look at some little small volume around that location, I can say, well, look, obviously the bigger the volume, the more mass is being created in it. But so per unit volume, how much mass is being created in that general vicinity, right? And that's what divergence is. That's the way to think about divergence. And the common term is to say that we're talking about a source, a fluid source. Right? I mean, we have spontaneous generation of stuff. Stuff is coming from somewhere, and so we're talking about the source of the fluid. There's different ways, different metaphors you could imagine here. Let me list off a few. Somebody has left some chemicals in a bucket, and so there's a spontaneous generation of a gas. Someone has left some little insect eggs in a aquarium filled with water, and the eggs are hatching. And so there could be a flow, an outward flow, steady state outward flow of little buggies, right? They hatch and they start swimming, and that creates this flow of bugs, right? One of my favorites, light bulbs. Light bulbs generate stuff. They generate a fluid called light. Right? If you think about it, it's not like light bulbs have like a supply of photons that they're shooting out like ping pong balls, right? That's not how light bulbs work. There's no photons in there. Light bulbs spontaneously generate photons, thus creating this flow of particles, aka a fluid. Anyway, I think that's a pretty good one as well. Okay, so anyways, I think of divergence in these contexts as being source density. And the opposite, if it's negative, people talk about sinks, and so I think of divergence as being sink density if it's negative. So sources and sinks is extremely common terminology, and divergence tells you how much of that is happening locally near a given point. Okay. All right. So moving along, I want to talk about gravitational fields now. This is a big example of physics applications of the divergence theorem. There's several results that we need to talk about. By the way, you may be thinking to yourself, I have no plans to become an astronaut, and so I don't really see why I need to be able to understand gravitational fields of large planet-sized thing. I mean, gravitational fields. The gravitational field created by this stylus is practically negligible. I mean, who cares? Nobody cares, right? There is no electronics that you may be interested in building that the functioning of which depends on the gravity created by some little small thing. It's completely irrelevant to that kind of stuff. And yet I claim that it's going to be a very important discussion. Anyone majoring in engineering, anyone interested in electronics, this is going to be a very important conversation, and I'm gonna hold for the moment why that is, but it ends up being extremely important. Okay, so let's just think about gravity. By the way, I like to start this conversation talking about gravity because it's so relatable, right? I mean, if you want to work on electronics, you're thinking about electrons and electric fields and magnetic fields and this kind of thing, and it's all pretty abstract, right? People didn't even notice these things until pretty recently, really, in the big scheme of things, right? Gravity, people noticed a long time ago, right? I'm pretty sure my dog understands gravity, right? At least, maybe not in this sense, but at least in terms of his experience, he knows if he jumps off the couch, he's going to go down to the floor, right, and not fly up into the air. So very relatable. All right, so let's talk about gravity first because it's so relatable. Here's the force of gravity that you might have learned in a high school physics class. This is, you can see right here, talking about the magnitude of the force. The problem with this expression is it doesn't represent the fact that force is a vector. Force is a vector. Right, so how do I make this a vector? And by the way, how do I make this a vector field? Y'all have heard about gravitational fields, Gravitational fields are the recognition of gravitational forces as a vector field. You know, wherever you are, there is a vector representing gravitational force. Okay, so here's how you do that. This is what I'm going to call the gravitational field. And you'll notice that there's that gravitational constant, and there's the M1. A couple of issues I want to get to. Where's the M2? Where did that go? It doesn't seem to be in this next formula. I'm leaving off M2 because I would like to talk about the gravitational field created by a single mass. In other words, the Earth creates a gravitational field independent of how much this thing weighs that gravitational field then acts on. So really, I would like to think of this as being acceleration. It's except for the fact that I haven't multiplied by M2 yet, this is really acceleration. And then, of course, if you multiply both sides by M2, then you get a force. This becomes a force. That is the gravitational force. All right. So, nevertheless, we're only going to talk about the acceleration as being the gravitational field, again, because I want to be able to focus my attention on a single thing that creates it. Okay, and what's up with the cube here, you ask? Right? Isn't it supposed to be a squared? How'd that happen? And this is actually pretty easily resolved. It's a little bit of algebra that we need to recognize. So let me come down here to write this down. I'm going to rewrite this as negative g m1 over magnitude of x squared times x over the magnitude of x. So the reason we have to put a cubed in there is because one of those goes into making this a unit vector. Right, so with this formula, even though it looks wrong, you've got a cube. Hey, what's with the cube in the denominator? All that's saying is we have an inverse square gravitational magnitude times a unit vector representing direction. So this is actually inverse square. It looks like it's not, but it is. This is inverse square. Is everybody on board? Okay. All right. Okay. All right. Now here's a flashback. Y'all remember in the section on partial derivatives, I wanted to persuade y'all how useful partial derivatives are, and so I had you compute various constructions involving partial derivatives, right? You were computing the heat kernel and the Laplacian and the, oh my gosh, there's so many partial derivatives, so many this, that, and the other algebraic constructions that involved partial derivatives. The point there was to show you how everything's written in terms of partial derivatives because they're so easy to compute. Right? So one of the things y'all did was compute the divergence of a vector field that is morally equivalent to this. It was a constant times the x vector divided by the cube of the magnitude of the x vector. I don't know if y'all remember that one, but if you flip back to section, 4.4 maybe? One of the exercises was, except for the constants, exactly this. And the result that you were supposed to have come to was that divergence is equal to 0. Obviously not at the origin. This vector field's not even defined at the origin. But everywhere else the divergence is 0. So anyway, I want to flip back through your old homeworks and notice that you've already done that calculation. It turns out this result is extremely important. I'm going to show you how important this is by using this fact to derive some remarkable facts about gravitational fields. It's very cool. Okay, first one is kind of an easy one. Suppose we have an object M that's outside of some region. Here we go. Here's my object M. It's outside of this region here. Now this object M, let me use some colors. This object M creates a gravitational field. Gravitational fields, as you know, are stronger closer to the mass, and they're weaker as you get further away from the mass. They always point toward the mass. Right? Again, familiar? Relatable? Right? Jump off the sofa, you go down toward the mass, down toward the center of the Earth. So here's the question I want to propose. Given that there is a piece of mass creating a gravitational field everywhere in space, and given that I have some region with a boundary surface there in yellow, how would I compute the amount of flux of this pretty weird-looking gravitational field? I mean, let's go back up and remind ourselves of this formula. It's got a square root cubed in the formula. Right? This is an ugly gravitational field, and I want to compute its flux through this kind of ugly surface. Everybody see the question? Looks like a hard problem. I mean, straight up, if you chapter 5 this problem, it's brutal. Parameterize that kidney bean surface. Ugh. Nightmare. Okay, so let's chapter 6 it, though. We want to compute flux through a boundary. Gauss's divergence theorem is perfect for that. I can compute the triple integral of the divergence of that field. Oh, wait a minute. The divergence is 0. We're doing a triple integral of 0. The answer is 0. And we're done. Yeah? Everybody on board? This is pretty cool. I mean, now, a neat fact, gravitational flux is 0. Where that came from is the fact that the divergence is 0 away from where the mass is. Now, I do have to emphasize, it's very important that the mass is way over here. Right? Because we're doing a triple integral. I mean, the Gauss's divergence theorem happens on this, this region and its boundary. So this is where, if I'm going to cite Gauss's divergence theorem, this is where I've got to make sure that everything is continuous and well-defined and nothing weird, nothing problematic. And, of course, on this blue region and this yellow boundary of that blue region, everything's fine. The vector field is perfectly well-defined, no issues. Sure, the vector field has a nightmarish singularity over there where the mass is. Not our problem. Everybody on board? Okay, so now, next question. Let's see here. What if the object M is inside of the region R? So here's the picture. Suppose, again, we've got this blue region, and it's got this boundary that I'll again put in yellow, and suppose the mass is there. Now, there is a temptation that you have to avoid to say, oh, well, if we're still interested in computing flux, flux is a triple integral of divergence. Let's just write that down. The divergence is 0 everywhere. Oh, well, okay, the divergence isn't 0 at the purple point. But, I mean, in the triple integral that we're doing a triple integral over this whole region. That's just one little itty-bitty point. Come on, how important could that be? There is a temptation. But it's that's the call of the devil. That's wrong. It's very important. These theorems, I mentioned this in passing at one point, but these theorems, Gauss's divergence theorem, fundamental theorem of line integrals, all these theorems that we've seen, very delicate. Everything in sight has to be nice, or else they do not work. And it's not even close. By the way, you should have seen some examples in Calc 1 classes of, the fundamental theorem of calculus itself is very delicate. If you have a function that has a derivative, everywhere except, there's one point where there's a discontinuity. How important could that be? Oh, but the fundamental theorem of calculus crashes and burns, and it's real easy to make counterexamples of this, right? Anyway, think about that one. Carefully. And by the way, if you haven't seen such examples, come to my office hours. I'll be happy to show you one. Okay, so we cannot make this argument as we did before because we have a discontinuity of the gravitational field. This point there means I cannot take a triple integral over this interior. So the fix is to say, okay, fine, but I can take a triple integral on this region. Let me burrow out a little hole inside of there. And let's talk about this region that I'm calling R0. Right, the boundary of R0 consists of two chunks. The boundary of R0 includes the boundary of R in yellow, right? And it also includes, that surface there, that sphere, right? So here's the good news. This region R0 that I have in blue does not contain the point where the mass is. The gravitational field created by that mass is perfectly decent, continuous, no problem on that blue region, R0. And I can write down Gauss's divergence theorem on that region, R0. Okay. Here we go. Now let's talk about what we just talked about. Let's see here. Our the boundary or R0 we just talked about it's the boundary of R, but also S, oriented negatively, oriented inward. Right? So let's see here. Let me write this down. So boundary of R minus S is what R0 is. The boundary of R0. Here, let me do it like this. So the boundary of R0 is that region. And Gauss's divergence then says flux through the boundary is equal to triple integral of divergence. And, well, we already know that divergence is 0, and so we get here 0. Now, there's a tempting lure to celebrate here and say, hey, we're done, right? The flux is 0. That's not what we just showed. What we just showed is that this difference between these two fluxes is 0. We did not show anything about the flux that we're actually interested in. But importantly, what we have shown is that the flux that we're interested in is equal to the flux through that sphere, the flux through S. So let's go back down to this picture. The flux we're interested in is equal to the flux through that sphere S. And I make the following observation. Notice that the flux through S, I constructed S to be a sphere around my mass. The flux through S does not depend on where that mass is. Watch this. Again, one of the nice things about having this touch screen is that I can just take this and go, whoop, how about over there? Right? So let's suppose this had been our situation. We had a little piece of mass way up there. I could still burrow out a little hole, right? This little orange boundary surface there. And I could still make the same argument. And how much flux is there through that orange sphere? Well, who cares that I moved it over there? It's the same amount of mass. It's creating a morally equivalent gravitational field. The sphere is in relation to the mass in the same place. It doesn't matter where the mass is. The calculation of flux around a sphere that encloses it is always going to be the same thing. So what we've shown here, we have not calculated what we wanted. I still don't know what. I still don't know what this thing is. What I've shown is that the flux is independent of where the mass is, and that ends up being a really valuable fact. Completely independent of how that mass is distributed. So, if you have a surface and with a bunch of mass inside of it, and all you want to know is the flux. All this mass, it creates a gravitational field. You just want to know the flux through that surface. Take that mass on the inside, move it around to your convenience, and it won't affect the flux. It'll change the gravitational field, of course, right? Gravitational fields change when you move them, but the flux through that surface won't. So, neat fact. Okay. All right. These two observations that we just made, let me remind you. If the mass is on the outside, it makes 0 flux on the surface. If the mass is on the inside, there's going to be some flux through that surface, but it doesn't matter where the mass is, and you can just move the mass around at your convenience. Okay. Those are our two big results. All right. It turns out that's exactly what we need to address this next question that I've written about here, and let me just walk you through what this is saying. What this is addressing is a very difficult question of, suppose I have a distribution of mass. So this is my attempt to draw a distribution of mass, and I'm going to try to make it non-uniform. So look, there's a lot less mass here. There's more mass there. In fact, let me thicken that up a little bit. We'll say that there's, some more mass in this corner over here, and it gets even more dense the more you get towards the middle, or toward this corner here. So, non-uniform distribution of mass. Each point in this mass, each atom in this mass is creating its own gravitational field. Oh my gosh, let's draw some just for effect. That little atom right there is creating a little bit of a gravitational field. Right? This atom over here is creating a gravitational field. At this point, there's a certain amount of gravitational field coming from that piece of mass, and there's a certain amount of gravitational field coming from that other piece of mass. At that red point there, at that little dot, you're getting gravitational field from that atom and from that atom, but it's much worse than that. Also, all these other billions, trillions of other little atoms, they're all creating their own little individual gravitational fields that are acting at that one red point. So if I ask the question, what is the total gravitational field at that red point? It's unthinkable, right? You're going to add up all infinitely many gravitational fields. Sounds like a really hard problem. And it usually is. And there's different ways to approach it. I'm going to do a calculation here, though, that is, I think, quite phenomenal. I'm going to take it a step further. Not only, let's say this. Imagine how hard it would be to compute that gravitational field. And now, if you have computed that gravitational field, imagine how hard it would be to compute the divergence of that gravitational field. That's even more work, right? And I'm actually going to do that. And it turns out the answer is easy. It's shockingly easy. And this is one of the reasons why, the applications of Gauss's divergence theorem to gravity are unbelievably powerful. It's this calculation right here. It's totally awesome. Okay, I'm going to compute the divergence of the gravitational field at that point. And here's how it works. It's a mathematical bank shot. I'm going to start by computing something that's not exactly what I'm interested in. I'm going to start by saying, well, let's look at a little ball. Let's look at that little ball there. And I'm going to compute the flux, the gravitational flux through that ball. Right? Okay. Now, reminder, we just did a couple of calculations of flux. Right? What's the flux under these circumstances? And we just made some conclusions anyway about, what's the flux under those circumstances. So we have, we have tools for computing flux. I'm going to use those tools in application to this situation. Here's my first one. I've already shown that to the question of flux, right, if I'm interested in computing how much flux is there through that surface, the mass outside of that surface doesn't matter. So I get to erase all of that. All that mass was outside my surface. Right now, sure, there's still some mass inside. Right? But all the mass that was outside, it doesn't matter at all to the computation of the flux through this purple surface. Right? That's this argument here. Everybody remember this argument? Okay. All right. Okay. That's nice. What about all that mass on the inside? Well, this argument tells me that I can take all that mass that's on the inside and I can reapportion it however I want. I can say, it was sort of evenly distributed through there. Let me just take all that mass that was on the inside and throw it in the middle. I can reorient that mass on the inside however I want. It does not affect the flux. Keep in mind, I'm computing flux. Eventually, I'd like to compute the divergence, but for the moment, I'm computing flux. So our problem just got crazy easier, right? Because of these two preliminary calculations here. Mass on the outside doesn't matter. Mass on the inside can be anywhere at once. Okay. So we have a brute force problem here. There's a point with a bunch of mass at the center of a sphere. How much gravitational flux does that create through the sphere? And let me, I guess I better zoom for drawing this next thing here. So that mass creates a gravitational field. It's all located at the center. Spheres have lots of symmetries. The distance to the center is constant. Whatever the radius of that sphere is, let's call it r. All the normal vectors are perpendicular to the surface. That means they're parallel to these field vectors pointing toward the center, well, away from the center. So it's just chock full of symmetries. And that allows for the following calculation. This is just immediate applications of the ideas we've just talked about. Let's see. I want to compute flux. Y'all remember chapter 5? There it is. That's what flux is. ds is in ds. Old news. Let's see here. Our gravitational field is that. Our normal vector is just a unit vector pointing in the direction of the position vector, right? That's, again, spheres are great in the sense that normal vectors are always in the same direction as the position vector. We've talked about that symmetry previously. So I haven't really done anything clever yet. This is just sort of plugging in to the flux that we're interested in. Now, let's see here. Let's go ahead and take this next step. Notice I have here x dot x. That gives me magnitude squared. I'm dividing it by magnitude to the fourth. I mean, the magnitude of x is all over the place in this calculation. And keep in mind, we're talking about a sphere. On a sphere, the magnitude of your position vector, it's the radius of the sphere, right? Spheres are awesome. So we have magnitude squared divided by magnitude to the fourth. That gives us altogether, that gives us 1 over r squared. That's all it is. These constants, of course, come along for the ride. Surface area, you may recall, surface area of a sphere is 4 pi r squared. Hey, you know, what's interesting to me is you look at this calculation and at a glance it's like, oh wow, look at all the funny symbols, and it's, oh my god, that's intimidating, right? If you were to, pull out a sheet of paper with this on it and show it to somebody and say, here, make sense out of that. It'd be scary at a glance, but notice not much has really happened here, right? I'm just plugging. I mean, this is established formulas. Here I just plugged in stuff that we know about gravitational fields and spheres, and I made this observation about, these are straightforward, ultimately. So anyway, don't let the, I know it looks very intimidating, but don't let the look intimidate you. Just, the way you understand stuff like this is just take a deep breath, take one step at a time, and realize that each individual step as you go there's a reason for it. You just have to identify what that reason is. As you can see coming, this r squared and that r squared cancel, and what we get is this result that the flux is proportional to the mass. Really great result. The flux, there's a bunch of constants in there, sure, but the flux inside of this sphere is just negative 4 pi g times the mass. Really simple result. Yeah?
And the mass is just the sum of all the mass within the sphere?
Within the sphere. That's right. Yeah, exactly. And now it's going to get even better. Remember, our original goal was to compute divergence. Don't forget, we also know that divergence that flux is computed by divergence with this triple integral. And keep in mind, we're looking at a very small little sphere, right? The mass is distributed over everywhere, and lots of regions of mass. But we chose to look at a very small sphere, and on a small sphere, divergence is approximately constant. You can factor it outside of the integral. The integral of dV is just volume, and so you get this. So flux is equal to that and that. Solve for divergence. You get mass divided by volume, which of course is density. And there you go. We've computed the divergence of this gravitational field. I mean, it seemed like we were up against this impenetrable, the near infinitude of number of different particles, all with their own gravitational fields, all of which are ugly. And then you want me to add those all up, and then you want me to compute the divergence? Oh my God, it seems insurmountable. But here we are. This shocking result. Does everybody see how this came together? Totally awesome. Okay, so this is a big deal. This is a really big deal, and this is something you want to make sure to memorize for no question about it. Any gravitational field, anywhere, I don't care how much mass is in the vicinity, and there could be non-constant, asymmetric, whatever. The divergence of the gravitational field is proportional to the density of the mass. And now I'm going to say that a little bit differently, as I wrote down here. Let's see, where did I? Keep in mind, divergence is flux density. So what this equation says is that flux density is proportional to mass density. So this is a statement about two different densities. These densities relate to each other. And another way to say that is, if flux density comes from mass density, flux comes from mass. And this is really fundamentally a true thing. So this, sure, mass creates gravitational fields, and the gravitational field, it's different everywhere, it's complicated, depends on where you are. But fundamentally, as soon as you put a box around it, right, mass creates flux, and it doesn't matter the shape of the box, it doesn't matter how big the box is, mass creates flux in any box. So I think that's a nice point of view. And there's more to say about the physics of that we just don't have time for, but really fun stuff. Here's yet another result. Flux is what it is. Divergence theorem, everybody recognizes this. We just showed that on the previous page that divergence is proportional to mass density. I haven't said anything here that isn't already long established, right? Whatever region you have, there's what flux is. Gauss's divergence theorem. We just showed that divergence of the gravitational field is proportional to mass density. These are constants. They factor outside of the integral. And an integral of density is mass. And so we have an even sort of more general result. Not only is it true generally, no matter where you are, that divergence of the gravitational field is proportional to mass density, it is also true no matter what surface you're looking at. Boundary surface, excuse me. Whatever region you have and its corresponding boundary surface, the gravitational flux is negative 4 pi gm. Now you may think, didn't we see that formula on the previous page? And kind of, but not really. When we wrote this, flux equals negative 4 pi gm, this was strictly on a sphere. We only showed this result on a sphere, and we took massive advantage of the fact that it was a sphere to do that calculation. So that was a relatively specific narrow calculation here. What we have now is that, in fact, it's true for any solid. Gravitational flux proportional to mass. Okay, so here's a quick application. Again, not that any of y'all are going to... look, if you want to be an astronomer, that's great, right? But probably, most of y'all are probably not. But nevertheless, just because it's easy to do, let's suppose we have a surface that's an outward-oriented sphere centered at the center of the sun and a radius of 100 million miles. A great big sphere, right? What's the total gravitational flux through the surface? Now, the Chapter 5 approach to this question is to say, well, the sun's creating a gravitational field, and I got to compute its flux. And Mercury is creating a gravitational field, and it's off-center, so I can't make any symmetry arguments with the gravitational field that's being created by Mercury. So computing its flux through this sphere is going to be a problem. Ditto Venus, ditto Earth, ditto Earth's moon, and I guess that's it. So that's there's the occasional asteroid. We're going to ignore that. Right? The overwhelming majority of the mass is in those objects. There's, what is it, 4 or 5 objects? 5 objects. And so still, the Chapter 5 approach to this question is I've got 5 separate gravitational fields, 4 of which are not symmetric, through which I'd have to compute fluxes through this surface. And that would be a tedious calculation, times 4, plus a little bit. For the sun, it's symmetric. It's easier. Right? But we don't have to. The flux is just negative 4 pi gm, end of story. Just add up the masses, multiply by negative 4 pi g, walk away. Very powerful. Everybody on board? Okay. All right. Here's another calculation. This is one of my favorite calculations in the course. I know I say that a lot, but this is really a good one. So this is what I like to call the Death Star problem. I used to call it the Death Star problem, and then Star Wars became it kind of disappeared from social visibility. It was kind of an old thing, and now, of course, it's kind of back. So here's the Death Star. Does everybody? Y'all have seen Star Wars now, right? Okay, just checking. Okay. Sorry, some of you haven't? Okay, I'm sorry. All right, so here's the general plot line. No, I'm kidding. But the all you need to know is that there's this object in the movies called the Death Star, and it's a satellite, right? But it's a man-made satellite that's the size of a small moon. It's a spherical thing, and it's got a certain amount of thickness, and there's hallways and people, bad guys mostly, walking around inside the thing, right? But it's spherical in shape and extremely massive, and has a thickness. So it's not, a sphere is just a surface. This is actually a shell, right? It's got a thickness to it. Okay. And so there's a lot of mass in play here. Again, this is planet size. It's made of metal. Of course, it's got a gravitational field. What is that gravitational field? This is not a single point, right? And so we're going to start off with is, let's start on the inside here. Let's look at that point P. I would like to compute what is the gravitational field at that point. And again, seems really hard, seems insurmountable, because this piece of mass right there creates a gravitational field at that point. And this piece of mass over there creates not as big, but a little gravitational field at that point. And ditto, this piece of mass creates a little tiny gravitational field at that point. And so again, looking at the entire mass of the Death Star, there's a lot of little pieces of mass, each of which are creating their own complicated gravitational fields at this one point P. So I want to add up all of those and figure out what is the total gravitational field. Seems like a hard problem. Okay. So let me try to handicap this a little bit. One argument that gets made, predicting in advance. A lot of people say, well, look, this is the mass that really matters. This is the mass that's closest. Closer mass exerts a stronger gravitational field. I feel like the gravitational field is going to point this way. But here's the thing. This mass over here, all of that mass, sure, it's farther away, but there's more of it. So there's a tug of war here, and the question is, who wins the tug of war? The close mass or the more mass? Anybody have any guesses who hasn't already read ahead to see the answer? I mean, what's your intuition, in other words? I just want to point out, it's a hard problem, right? If you had to handicap and guess, I think it's going to be toward the purple, or I think it's going to be toward the red. It's hard to decide. Okay. All right. So here's how this argument works. This is another one of these mathematical bank shots. We are going to compute what we're interested in by first computing something else. I'm going to start by computing. I'm going to take this sphere centered at the origin that goes through our point in question, and I'm going to compute the gravitational flux through that sphere. And let me give you the short version of it. The algebra is on the previous page, but the short version of it is this. First of all, everything's symmetric. This is a sphere, right? It's got the same, the shell has the same thickness everywhere, at least for our approximation. And so this is a symmetric situation, and so the gravitational field has to be radial. Right? You could, I mean, if the gravitational field pointed off axis, then that would suggest there's an asymmetry somewhere, and there isn't. Okay, so it's radial. It's also going to be uniform on this sphere. It's going to be the same magnitude everywhere on this sphere. Because again, the symmetries, right? I mean, if you take this shell of mass and if you rotate it around, you're not really changing it. This symmetric shell, when you rotate it, identical to where it had been. Right? So the gravitational field has to be the same everywhere. Does everybody see the argument there? All right. Well, here's how it goes down. Let's compute the flux through this blue surface. Flux is proportional to mass. There's no mass, right? I mean, flux is proportional to the mass inside the region. There is no mass inside the region. The mass is all over here. That's where the mass is. And all the bad guys. Right? So inside of the shell, inside of the blue sphere, no mass. No mass means no flux. So let's draw this picture again. This gravitational field, it has to be radial and symmetric, and yet it can't create any flux. How is that possible? As I've drawn here, this purple, symmetric radial field, that looks like it's creating a negative flux. Or if it went the other way, right? If it was like this, if that's what the gravitational field looked like, a positive flux. But the flux has to be zero. So it can't be either one of these. In fact, the gravitational field is just zero. That makes sense? That's the only way to be both radial and symmetric and have zero flux. So the algebra is just this right here, flux. The radial and symmetric we quantify by saying, well, look, it's got to be some function of distance times the x vector. That makes it radial. So this is just an algebraic way of saying that what I just said, that it depends only on the distance from the center. It's got this rotational symmetry, and it's radial. That it's some function of rho times the x vector. If it depends only on rho, then it can pop outside of the integral because it's constant on the entire sphere. X dot n is rho. It's the magnitude of x, which is rho. And this is something that we can compute. And altogether then, what you get is that this expression has to be zero that means that this has to be 0, and therefore our vector field has to be 0. It's a pretty neat argument. Okay, now the exercises at the end of the section have some twists on this. I'm going to ask you all to go through on your own. I'm pretty sure there's some recordings. There should be. I feel like I can't remember if there are, but anyway, if there aren't, somebody come to office hours and ask me. I'll be happy to go on at length. But so a next reasonable question would be, okay, what about at this point? What's the gravitational field at that point? Well, the argument you're going to make is you're going to make a sphere that includes that point. Now here there is a bunch of mass on the inside. You can write down exactly, well, you can just, the statement of the question will, tell you what the mass of the grand total mass of the Death Star is. It might just be capital M, whatever. And then again, you can make a symmetry argument, a radial argument, and you can compute exactly what this field vector has to be here. Same kind of a thing. Okay, so just strategically, here's the sort of the game plan. Mass creates a gravitational field. And this is a hard way to think about it. If you look at each piece of mass and think about, well, what is the corresponding gravitational field? Yikes, right? But the thing is, the gravitational field you can relate to flux. Flux relates to divergence. Divergence relates to mass, right? This is a result that we just derived, that divergence is proportional to mass density. This is Gauss's divergence theorem. Right, and this is chapter 5. So, yeah, don't go directly at it. Don't take the chapter 5 approach and look at each piece of mass and compute the gravitational fields and try to add them up that way. We have these powerful tools that relate mass to divergence easily, divergence to flux easily, and flux to the gravitational field by way of, symmetry arguments, for example, and this kind of thing. So this roundabout approach that we've just talked about make these kinds of questions possible. Okay, all right, so I think those are great questions. All right, now I'll remind you that I started off this discussion of gravitational fields with the assertion that it would help engineers beyond those who are going into being an astronaut or an astronomer. And here's how. Here's a formula you might have seen in high school. Formula for the force, electric force between two charged particles. And I just want to take a moment to acknowledge how super similar this is to the force of gravity. Product of two quantities you associate to particles, okay, charge instead of mass, right? But still, whatever. It's constants, two constants, some other constants, and it's inverse square in distance. And directly along the line between the two objects in question. Mathematically, it's identical to the gravitational field. It's the same formula. And so hopefully no surprises in how this all breaks down. You can write down the electric field as a vector field. Again, it's inverse cubed, or it looks like it's inverse cubed, I should say, but it's actually still inverse square. Same argument. You can talk about what the electric flux is, depending on if a particle is outside or inside. I mean, it's exactly the same arguments that we made going through the discussion of gravity. The big punchline is the divergence of the electric field is proportional to charge density. Just like the divergence of the gravitational field is proportional to mass density. Divergence of the electric field is proportional to charge density. And again, taking an integral on both sides, this is sloppy notation, forgive me, but triple integral of divergence gives you flux. Triple integral of charge density gives you charge, and thus we end up with this formula, that the total flux of the electric field is proportional to the total charge inside of the surface. The math is all exactly the same as what we just walked through. So I think this would be a great exercise. I would like to encourage y'all to derive this fact that I have circled in blue. I've hit the highlights for you here. Feel free to cheat, by which I mean shamelessly rip off the arguments that we just made about gravity, because it's the same, right? It's the same exact thing. It's just with different constants. Sure, different constants. But structurally, the argument is identical. So feel free to, have, the gravitational argument over here and just, okay, all right, well, let's see, what was the next step? All right, now there's different constants over here, but we're taking a flux. Okay, well, let's write down flux. And it's the same. Just I want you to go through and just kind of one step at a time, notice that the same argument derives this result. Okay. All right, so there's another statement that you can make about magnetic fields. I'm going to be super quick on this. Magnetic fields are also of interest in physics. It's harder to derive the formula for the magnetic field. It depends on velocity, so it's a little weird. As much as I would like to, I can't just go off and do a bunch of physics. Anyway, the punchline, though, is the divergence of the magnetic field in a steady state is 0. And again, taking a triple integral of both sides, triple integral of divergence turns into flux. Triple integral of 0, of course, is 0. And so you get these two statements about magnetic fields. Okay, very last thing. There is a two-dimensional version of Gauss's divergence theorem. I never have time to present this in class. It's always something that I have to, leave as an exercise to the reader. But you'll notice it starts off with an accumulation argument, cancellation on this edge, opposite orientations. I think it's going to be very familiar. And the result that it gets down to, also a familiar result, two-dimensional Gauss's divergence theorem, and the only real difference is that divergence now has only two terms in it because it's two-dimensional and therefore there's only two components of the vector field. But it's morally equivalent formula. So anyway, give this a look, and I'm going to declare us to be done with 6.4. Okay. All right. See y'all later. Oh, and I have homeworks to return, and some of y'all came in after I started the lecture.